All right, folks, welcome back. Took a little break to deal with grading the bone tests and getting the bone tests all arranged for us, but we're back. You'll notice that there's a photograph of an older gentleman. This is apparently a 74-year-old professor at the University of North Carolina who did his lectures to an empty classroom through Zoom. And apparently, he didn't want to just lecture to nobody, so he brought along a puppet, if you see in the front table, to keep him company and to have him somebody for him to have somebody to have eye contact with. So I thought, well, that's kind of a neat idea because I've been really struggling to a point, having to lecture all by myself. So I got a group together to keep me company so I can look out and have an audience. It's not nearly as interesting or fun as you guys, but there we go. We've got some friends to keep us company. So this is where we left off. This is a diagram of a skeletal muscle fiber. We'll remember that a skeletal muscle fiber is a cell, right? Fiber and cell mean the same thing. And there's lots in this diagram, and you're going to see this diagram often in your textbook, in our lectures, because there's a lot going on here. You'll remember that we have sarco as our root, that means flesh or muscle. So that kind of orange edge was the sarcolemma, or the plasma membrane of the muscle fiber. The yellow tubes were the transverse tubules that allow for a nerve impulse, because we need the nerve impulse to get a contraction going, to allow the nerve impulse to get deep into the muscle fiber. Suspended between two adjacent transverse tubules is the sarcoplasmic reticulum. The sarcoplasmic reticulum was a specialized version of the endoplasmic reticulum, and its main job is to store calcium ions that are going to play a really big role as we move forward. You also see what I refer to as loaves of bread tucked in there. Those are our many, many mitochondria. So please refer back to the slide where we talked about the differences between sarcoplasma, the cytoplasm in a skeletal muscle fiber, and good old-fashioned cytoplasm, that there is in fact a difference. So moving on from there, what else are we going to find in our muscle cell? We said that we were going to find myofibrils, and there were two kinds, and they were described or named by their description, thick and thin. The thin myofilaments are also referred to as actin molecules. The thick myofilaments are referred to as myosin, and why they're called that will become apparent very shortly. So when we look at our myofibrils, we have our actin or our thin myofibrils. These are composed mainly of the protein actin. Virtually everything we're going to be talking about in this lecture refers back to some description of protein, some type of protein. These actin proteins are arranged in two strands that are wrapped around each other. If you're old enough to remember Barbara Bush, she was George W.'s mom and regular George's wife. As First Lady, she always had pearls on, and there were typically two strands, and they were wrapped around each other. So that's what we're talking about. I'm going to have a diagram in a second. Each actin molecule contains a myosin binding site or a myosin active site. What these molecules are going to look like, what these actin molecules are going to look like is a black-eyed pea. So we'll go to the next slide, and then you can see what we're talking about. All right. So we've got two strands of what I refer to as grape jelly beans. Right? And you'll notice that those grape jelly beans have darker spots on each of them. That's the black eye of our black-eyed pea. Okay, that darker spot is representing the myosin binding site or the myosin active site. So each jelly bean is an actin molecule, and each actin molecule has a binding site. That's going to become important when we're doing our contraction, because that's where the protein myosin or the myosin myofilament will attach to the thin myofilament. We're also going to find two other proteins that make up the thin myofilament. That's why the name actin is kind of misleading, because it makes you think that there's only actin molecules contained within it, but in fact there are three: actin, tropomyosin, and a third. Tropomyosin covers the active sites on the actin. I refer to them as licorice whips. They're those orange kind of strands that you see that are positioned directly over top of the active sites. Each tropomyosin molecule covers 7 active sites. So it's going to cover 7 actin molecules. And don't count, trust me, it covers 7 active sites. I wouldn't lie to you. And our third protein that's going to make up our thin myofilament is troponin. You may have heard of troponin if you work in a clinical setting. If someone goes to the ER or they're on a cardiac care unit and it is suspected that they had a heart attack, one of the things that is checked for are troponin levels. If there's an elevated troponin level, it is indicative of muscle damage. As we'll talk soon, our cardiac muscle is set up, built exactly the same way as skeletal muscle cells. So they have a large component, a large amount of troponin that make them up. So in a heart attack, if there is damage to the heart wall, the myocardium, the muscle cells that make up the heart, a patient would have elevated levels of troponin in their blood. So that's one of the first things that are checked when somebody comes into the ER with a heart attack. Well, this troponin has a high affinity for 3 things. Affinity means, what do you think affinity is going to mean? It means it likes these 3 things an awful lot. It wants to hang out with them an awful lot. One of the things is actin, which makes sense. Okay. Oh, and the troponin, I'm sorry, let me back up. The troponin are those lemon heads, those yellow structures in there. So the troponin has a high affinity for actin, which is good because it hangs out with actin. And tropomyosin, again, it hangs out with tropomyosin. And again, those darn calcium ions, they're rearing their head yet again. We have a specific area for storage for our calcium ions, and now we have troponin, whose job it is to want to hang out with calcium ions. So it's a recurring theme. So there really must be something important about these calcium ions. Our second myofibril are the myosin, or the thick myofilaments. We say that these myosin molecules are golf club shaped. All right, so you'll see that there's a handle. The diagram refers to them as a myosin tail. That would be kind of the shaft of the golf club, and the myosin heads are the head of the golf club. Now, this kind of falls apart for 2 reasons. There's 2 myosin heads per molecule, and each golf club only has 1 head. And each myosin molecule has a hinged area, which, if you think about what a hinge does, it allows for the movement of something, right? You have hinges at the door so you can open and close the door. This hinged area is going to allow the myosin head to move back and forth, which is going to be crucial to how our molecules are going to move when a contraction occurs. These heads contain something called ATPase. Hopefully, ACE, the ending ACE, reminds us that we're talking about an enzyme. Very good. And what this enzyme is going to act on is, that's right, ATP. So ATPase is going to be an enzyme that is going to work on ATP to break it down. Well, why would we want to break down an ATP molecule? What does an ATP molecule have to give? The whole reason we have ATP, it has energy to give. So by having ATPase available, we can get at that energy stored in an ATP molecule. As we said, the head of our myosin molecule is attached by a hinge. This allows us to have movement at that hinged area. The head of the myosin molecule binds to the myosin active site. The myosin active site is on the actin molecule. So what we're saying here is we're going to have a connection. We're going to have a physical link between our thick and thin myofilaments, and that connection is going to be through the myosin head binding to our actin active sites. This is a page from your textbook. This is really a wonderful kind of down and dirty 1-page document that includes a lot of stuff that we've talked about in several lectures. You will notice we start at the top with a muscle as a whole. It labels for you our connective tissue coverings, right? Our epimysium, paramysium. It breaks down a fascicle and it brings it all the way down at the bottom to our myofilaments or our myofibrils. And we see how our thick and thin myofibrils are arranged. And that's what we're going to talk about now, is that arrangement, which we call a sarcomere. A sarcomere is a basic unit of contraction. This is where, getting down and dirty, this is where the contraction is going to happen, right? We look at a muscle like a big bicep or your gluteus maximus, like a really big muscle, and you think, well, gosh, how does that whole muscle contract? It all comes down to this little tiny itty bitty piece of a muscle fiber that allows for contraction to happen. It's really pretty fascinating. Neither type of myofibrils run the length of a fiber. Again, I know I'm beating you over the head with it. A fiber is a cell. And again, our skeletal muscle fibers are very, very long cells. That's one of the things that make them different from other cells. Our myofibrils are our thick and our thin myofilaments, right? So what we're saying here is neither the actin nor the myosin is long enough to go the whole length of a fiber. Okay, so running the whole length of a fiber, we're going to have many, many, many sections that we break that down to, and those sections are called sarcomeres. And that's where we're going to find a very specific arrangement of our thick and thin myofilaments. And again, here's that same diagram we talked about. You'll notice that if you look carefully that there's Z discs. That's from one Z disc to the next, that's one sarcomere. That's one unit that we can talk about. And that's what we're really going to focus in on, literally and figuratively. And again, if you go back to table 11.1, it's going to give you a really good overview of this thing called a sarcomere. And we've choked way down. We're really, really focused in on this very specific part because these individual sarcomeres are going to be where we have contraction. This tiny little section is what allows you to lift a very heavy object. So our individual sarcomeres are both separated by and connected by Z discs. The Z discs are the end points of each of our sarcomeres, but it's also the beginning of the next one. If we were in our lecture hall, what I would use is the wall between the two lecture halls, right? It's a common wall. It acts as the boundary of our lecture hall, but we share that common wall in between, right? We use one side of it, the other lecture hall uses the other side of that same wall. That's what we're talking about with our Z discs. So what are we going to find in a sarcomere? What makes up a sarcomere? We have our Z disc. Connects adjacent sarcomeres. Adjacent is next door, so that shared wall that we talk about between our lecture halls. Our myofilaments attach here. Both our thick and our thin myofilaments are hooked onto, attached to the Z disc on either end of our sarcomere. We have our A band or our anisotropic band. This is the area of overlap between the thick and the thin myofilaments. This is where we have this section. We're going to find both thick and thin myofilaments. We're not going to see that in every section of our sarcomere, but in the A band, that's where we see it. Now, I always have a tough time as to, is the A band where it's dark or is the A band where it's light? So I came up with kind of a silly thing, and for the A band, because there's an A, it's the A band, it's dark, right? Dark. So it's going to remind me that the A band is the thick area where we've got that overlap of both types of myofilaments. The H zone is the center of the A band, and this contains only the thick myofilaments, because remember, they're not going to run the whole length of our muscle fiber. We'll pick up with our I band in our next lecture.